Everyone, and welcome to the second session of the second quantum session for the fellows. So also welcome to people from who are joining us from Zoom from CIQC and QSA. So I should say that if even if you're on Zoom, you can ask questions either through chat or you could even ask a live question. So we'll start with Anurag Anshu, who will tell us about approximation theory in quantum antibody systems.
Thanks so much. Is the sound clear? Okay, great. So thanks again for joining. I'll be speaking about approximation theory in many-body systems. Well, the polynomials are the favorite objects of all computer scientists, and this talk is of similar nature, but in this particular case, I'll talk about a specific application of polynomials to physics-related systems. And I believe that there might be some results and applications that might not have been seen earlier. Apologies if someone noticed that the talk title has changed. I just thought that another talk on Hamiltonian complexity would be nice for the audience. So we'll be discussing about a certain class of systems which are known as quantum antibody systems in a physical setup. So for example, in this picture, you see a set of dots, which are a collection of particles. They're arranged on a two-dimensional lattice, and they're interacting locally, which is governed by the laws of nature. The laws of nature do not permit very long-range interaction in a strong way. So this sort of captures that property. So for example, here you can see that the interaction is localized to 4 spins. Like if you think of each placket as capturing an interaction. So how does this system look like mathematically? It is given by something known as a Hamiltonian, which captures the locality of these interactions. So here the Hamiltonian is a sum over I and j, which label the plackets under some labeling. And for each ij, the placket hij, let's say this red one over here, acts only on the particles in the placket and acts as identity everywhere else. So this set of systems or generalization of it have been extremely important in physics for over a century. There are a few states here which are particularly interesting. First is known as the ground state, which is the smallest eigenvector with the smallest eigenvalue. And this is where the system is expected to be at very, very low temperatures. Another states are Gibbs states, which look in this particular exponential form, and they describe the system at high temperatures. And folks from machine learning community and so on would recognize these as graphical models at all, also in a classical system. So these are all generalizations of that. But turns out that these states are really large. So if there are n times L particles in this picture, then these states are very big matrices of 2 to the n times L and 2 to the n times L dimension. And understanding their property is very, very rare. So in the past 100 years, I'd say, there has been rare cases where people have exactly identified what these states look like. Despite this complex state, it's quite remarkable that these states exhibit some general features. So one example is exponential decay of correlation, which I won't define it precisely, but one could recognize it in various domains as basically the correlation function between certain things that you're observing. Similarly, there are other properties known as area laws of entanglement entropy, and also classical simulation algorithms. Because the systems are so complex, people also want to try and simulate it. So these generic features have been popping up lots and lots of times. So in this talk, as I promised earlier, I'll be speaking about a particular role of approximation theory in these generic features. And the starting point is a collection of results that really appeal to me. So let me describe those. So in 2008, Hastings showed that the ground states of gapped Hamiltonians in one dimension, they satisfy an area law with an entanglement that scales as exponential in 1 over the gap of the Hamiltonian. This result was a major breakthrough in the field. And remarkably, a few years later, Umesh and co-authors working here at Berkeley, they exponentially improved this result to 1 over gap. There's another set of results. So Hastings again showed, well, now in the past, around in 2003, that the ground states satisfy what is known as a decay of correlation, which means that the correlation function, it gets weaker as the distance between things that you're observing gets farther away. And the rate of decay is given by the gap of the Hamiltonian. This result is tight for gapped Hamiltonians. But it turns out that in another work that came out very recent, not very recently, but 5 years ago, Huang and Gosset showed that this result can be improved for a special class of systems. So what are these systems? So this Hastings result was tight for a class of systems which are known as frustrated systems, which could be seen as the quantum versions of unsatisfied CSPs, for example. Huang and Gosset result, it applies to quantum versions of satisfied CSPs, which are known as frustration-free systems. And this improvement of square root of a gap was quite remarkable, in my opinion, because this was tight for frustration-free systems. So what underlies these results, both these improvements that I have shown here, is the same object, which is the Chebyshev polynomials, which comes from approximation theory. And it's quite remarkable that in these results that one can obtain almost tight results from the Chebyshev point of view, which in the prior applications using the techniques of Hastings required some highly non-trivial tools from analysis. So I'll be presenting, let me see how much time do I have. 5 minutes, great, yeah. So in the 5 minutes, I'll go over 5 slides and I'll be presenting my own work in this direction, pushing this line of research. So before that, let me quickly tell you what these Chebyshev polynomials are. So the Chebyshev polynomials, well, their role comes in the following way. So imagine a function f, which takes a large value at a certain x, let's say x equal to min, and is 0 otherwise. So clearly, this is a very, very complicated function. It peaks at a single point. Approximation to it is not possible with any low degree polynomial. But if you promise that you only care about approximation in a certain regime, then Chebyshev polynomials are known to be the best objects that achieve this task. And the bottom line is that f of h is the ground state of the Hamiltonian, and c of h is the best low degree approximation to the function. So that's where the Chebyshev polynomial morally comes in this whole area. So the first result that I talk about concerns the Gibbs states that I showed you earlier. In one dimension, these Gibbs states, which are very, very important in physics to predict the behavior at high temperatures, simulating them is a very standard task. And in heuristic methods, simulating them usually requires just linear time, linear in the number of particles. It doesn't take more than that. But any rigorous proof that there is a simulation method in the prior works required a lot of time. So for example, it required a high polynomial time to run. In a recent work with Kuwahara and Alhambra, we showed that for a large range of temperature, which actually matters for physical systems, this runtime can be strictly improved to almost linear. And this linearity simply comes from the optimal approximation to the exponential function that is obtained via Chebyshev polynomials. And certain features of these polynomials really help shape this near linear time behavior, which prior works did not have using other kind of approximations. Next example concerns a graph and a picture. I'm not very good at these pictures, but I'll try to relay the main ideas. So a certain interesting class of quantum states were discovered recently in the group of Misha Lukin. And this image is particularly taken from this work, which studies the entanglement behavior of these states. So in this picture, you see a many-body system. And each dot here corresponds to a quantum state, which is an eigenstate of the Hamiltonian. There are a lot of dots here, but what's the most interesting dots are the ones at the bottom, which form a curve. And those dots are known as scar states. They are somehow outliers in this picture. So this picture denotes, labels the energy eigenvalues in the x-axis and the entropy of these states, the entanglement entropy in the y-axis. And what you notice is that these states have particularly small entropy, which is a rare example, which probably was not believed earlier. At the same time, what you notice is that the entropy within these states gets smaller as you go to lower energy. It somehow peaks at the middle energy and then gets lower again in the lower energy. So we explained, so this is what happens. The entanglement increases in a nice way and then decreases again. So in a recent work, we explained this phenomena using polynomials again. This is not Chebyshev polynomials, but these are related polynomials. And I guess if I were to give a one-line statement to computer scientists here, especially those who are familiar with approximation theory, if you note that the OR function, which has Hamming weight 1, it requires a lower degree to approximate compared to the majority function, which has Hamming weight n over 2, which peaks at a middle point. So this is the same feature that is exhibited here. The entanglement in these states peaks according to the energy of the system, and that's exactly what is reflected in this in what we will see in the experiments. Next example will be about computing the spectral gap itself. As I mentioned, the spectral gap plays a key role in many of these systems, and so I'll be finishing very soon. And computing them is very hard. But then there is a class of examples that have been the class of techniques that have been developed. What they do is that they, instead of computing the gap on the full system, they try to compute the gap on a smaller set of systems. And if the gap is large enough in the smaller system, then you can prove that there's a large gap in the bigger system. So this relation between this local gap and the global gap, it has been explored a lot in the past few years. And in certain cases, it was shown that the tight relation between the two holds using some techniques that were there around main body system. In a recent work, I showed that this relation holds for all dimensions and all boundary conditions. And the source of this improvement that you see here comes again from Chebyshev polynomial as well. There's no surprise where this is going. Okay, so in the final slide, I'll talk about area laws, going back to area laws in 2D systems now. So in the 2D systems, area laws are very big open questions. And there's no proof yet that gapped systems in 2 dimensions, they exhibit area law behavior. Looking into this line of problems, into this particular problem, with Itai, Arad, and David Gossett, we asked the following question recently, which is, let's go back to the 1D systems. What is the optimal polynomial approximation to the ground states of 1D local Hamiltonian systems? As I showed, Chebyshev polynomial seems to be the optimal one as a function of the Hamiltonian, but is there something better that can be done? So what we showed is that if you assume certain property, first is the frustration-free assumption that I already introduced earlier, and next is the local gap assumption, which I introduced quickly in the previous slide, then a multivariate polynomial of the Hamiltonian can significantly improve upon the Chebyshev behavior when you're interested in very, very small error of approximation. And in fact, for those who are aware of approximation theory to OR functions or point functions in the classical literature, it turns out that these polynomials, they generalize, and in fact, they achieve the approximations that are given for the OR functions, and which were obtained a long time back by Karnley and Smolensky. So what's very interesting is that this approximation is exactly what's needed to prove an area law for this class of systems, frustration-free and locally gapped systems in 2 dimensions. And it's quite surprising why exactly do these polynomials serve the right tool? And the central question that we leave behind is that, is this approximation achievable for all gapped systems? If it can be done, then there would be basically, that would resolve the area law conjecture in 2D. So with that, let me quickly tell you about more applications. So even more recently, quantum circuit lower bounds have been developed using Chebyshev approximation and so on, and even the ground state preparation algorithms by these recent works. With that, thanks, and sorry for overstepping a bit.
Great. So questions while counter is setting up?
Do these fancier polynomials from the last couple of slides also come out of optimization in some way? Like Chebyshev polynomials come out of acceleration and things like this?
These come out, these are sort of derived from Chebyshev in certain way, but I don't think they have a optimization interpretation yet. It's not clear. That's my question.